Hello everyone, this is the first video in our playlist, and in this video we're going to talk about the open channel example. And we're given with a problem, and where we're given with the flow rate for the water and the width of the width of the open channel, and also the incline of an open channel, and we are asked to determine the height of a water level using a Python code. So we're going to use scipy.optimize.root to solve for height. But before jumping into the Python, we have to derive some related expressions so that we're going to use in our code. So here we have the diagram where we're given the three views of an open channel. So as you can see here, it's inclined at the theta angle, and it has a width of W and a height, and here H is the height of a water. Okay, and let's say where we have a length of an open channel to be delta X, and so the height, so the water is going to be the gravity driven, right? So the change in height which is delta Z, is going to be delta X times sine of theta, right? And because of the fact that it's open channel, if we say the top to be the first point and the bottom to be the second point, because of the fact it's being an open channel, the pressure at point 1 is going to be equal to the pressure at point 2. We're going to need that information later in our expression. So to start with, let's write down the Bernoulli's equation for our particular problem. So the Bernoulli's equation is going to be like P1 minus P, like pressure point 1 minus pressure point 2 over the density plus. So we know that we're going to be talking about one velocity, so change in velocity is going to be equal to 0, so we don't have to actually write it down. And so we're going to skip that term, g times z1 minus z2, right? Okay, so it is equal to so 4 times F, where F is the fanning friction factor, times delta X velocity squared over D, which is the diameter, times 2, right? Okay, so what we can do now is we're going to manipulate this equation to get the expression we want to use in Python. So let's try to divide everything by delta X and multiply everything by rho, which is the density. Okay, if we do so, what we're gonna have is this term plus, so this term has to be multiplied by the rho and divided by delta X, and we can also replace delta Z, so Z1 minus Z2 is equal to delta Z, right? And we know that our delta Z is equal to delta X times sine of theta, so we can replace that. So it's G rho delta X times sine of theta over delta X equal to 4F delta X times velocity squared times density over diameter squared, right? And delta X. Okay, so we can see here delta X's are going to be cancelled, and here we can also cancel our delta X here. And also, what we also know is it's an open channel, right? So the pressure at point 1 is equal to the pressure at point 2. So this term is also going to go to 0, which makes it easier. So because of these densities are also going to cancel. So what we're going to be left with is g sine of theta, where g is the gravitational acceleration, is equal to 2F, because 2 and 4 are going to cancel, 2F, where F is the fanning friction factor, velocity squared over D. Okay, so this is the expression we get for g sine theta using the Bernoulli's equation. So what we can do now is, here in the problem, we are given the most important assumption. So we're assuming the shear stress of the wetted wall to be equal to that for an equivalent circular pipe with the same average velocity. So let's draw a circular pipe with the water, with the fluid inside. which is in our case water. So we have a fluid inside, right? Okay, so let's try to do the force balance for our particular case. So it's gonna be, so force, it's gonna have a weight, right? So the weight is mass times the gravitational acceleration. And we can also express our mass in terms of height multiplied the cross-sectional area, right? So let's say our circle pipe is gonna have the same length as our open channel. It's gonna be delta x. So because if it's circular, it's gonna have a cross-sectional area same with the circle, right? So it's gonna have like rho g a times delta x. So where rho a delta x is going to be the volume and the mass, and g is going to be the gravitational acceleration, and it should be equal, so it's going to be in equilibrium, right? So it's going to be equal to the shear shear force. So shear, and that's going to be the shear stress on the wall multiplied by the vetted perimeter of a circular pipe times delta x. So here our delta x's are going to be cancelled. So our rho g is going to be equal to the shear stress times the vetted perimeter over A. Right? So let's talk about this term for a moment. So our vetted perimeter is going to be the perimeter, like the length of a pipe, like it's going to be this cross-sectional length, and so that's going to be equal, so our vetted perimeter over area is going to be equal like 2 pi r, and if we want to express that in terms of the diameter, that's going to be pi d, pi times diameter over pi diameter squared over 4, which is the cross-sectional area. So the pi's are going to be cancelled, d is going to be cancelled, so what we're going to have is 4 over d. So our g here is going to be equal to shear stress times 4 over d times the density. And what we can do now is we can get this g and plug into this equation, which we derived from Bernoulli's equation. So it's going to be the shear stress, like 4 times shear stress over diameter times the density is going to be equal to 2 times fanning friction factor, velocity squared over diameter. Right, so the diameter is going to be, okay, I forgot the sign of theta. Okay, so the diameter is going to be cancelled, right? So what we're going to have, so 2 and 4 are going to be cancelled, so we're going to have 2. So if we solve for shear stress is going to be fanning friction factor multiplied by the density times the velocity squared over 2 sine theta and 2 sine theta. Yep, that's it with our shear stress. And yes, so the next thing we are going to do here is, okay, we're going to basically work with this equation that we derived, but we're assuming that the shear stress is going to be equal to the one in with the circular pipe, right? So that's what we derived now. So this is the expression for the shear stress, and we can use it for our open channel. But the wetted perimeter in our channel is going to be slightly different. So the perimeter which the water is interacting with the wall is 2h, so it's interacting with the 2 side walls and the bottom wall, right? So it's 2h plus w, and the cross-sectional area that's water interacting with is going to be the h times w. So our wetted perimeter over area for our particular case with open channel is going to be 2h plus w over hw, right? Okay. So now we can use this expression here, rho g, and plug in shear stress to the one we derived, and vector perimeter over like area for the box. Okay, so the expression we're gonna have here is gonna be, let me write it down here. Okay, it's rho g is gonna be equal to fanning friction factor times rho velocity squared over 2 sine theta 2h plus w over hw, right? And here we can notice that the densities are going to be cancelled, right? And so our g is equal to fanning friction factor times the velocity squared over 2 sine of theta multiplied by, okay, let me write it, multiplied by 2h plus w over hw, right? Okay, so here that is the equation we can use in our root solver, so that we can solve for a particular value of h, which will make this equation equal to g, which is 9.81. But we have problems with our fanning friction factor and the velocity. So the fanning friction factor is the equation of a Reynolds number and the surface roughness, which we use this in our problem. Okay, so the Reynolds number itself is equal to rho times v times d over the viscosity, right? So the problem is with the diameter. We have a rectangular channel. It does not have a diameter, but it has something called the effective diameter. So how we can find the effective diameter is, so we're assuming that the shear stress is equal to the one with the circular pipe, right? So we can make our wetted perimeter over area to be equal to each other. So the wetted perimeter over area in in circular pipe was 4 over diameter, right? And the one in rectangular channel is 2h plus w over hw. So if we solve for diameter, it's going to be equal to 4hw over 2h plus w, which is going to be equal to the diameter. So that is the diameter we can use for our Reynolds number. So that's going to be the equation we're going to need. Okay, and the problem with the velocity is, we know that the velocity is equal to the flow rate over cross-sectional area, right? Because we're given the flow rate of a water. Okay, and the cross-sectional area in our problem is h, height times the width, right? So we can just replace it to our equation. So we have g is equal to fanning friction factor multiplied by q squared 2h plus w over 2 sine theta. So we already have one h times w, and we're adding 2 more, so it's going to be h times w cubed. So we can use this equation in our root solver. And how we determine the fanning friction factor is, in our previous videos we derived the expression, we used the expression which is the Churchill equation. So we're gonna find a particular value of Reynolds number for our case, and for that Reynolds number we're gonna use Churchill equation to get the fanning friction factor. And we have all the other variables given, so we can solve for a particular h, which will make our g equal to 9.81. So in the next step, we're gonna work in collaboratory to write the Python code and actually solve for our height of the water. So in this part, we're gonna jump into Python and run the code using the equations we derived in our previous part. Okay, so we're gonna go to collaboratory. As always, we're gonna start with importing our numpy and scipy.optimize. So we're gonna import numpy and from scipy.optimize library, we're gonna need the root function. Okay, and for our problem, the water is flowing the aqueduct, right? So we're gonna need something specific for the water. So the mu, which is the viscosity of a water, is equal to 1 times 10 to the power of -3, and the density of water is 1000 kilograms per meters cubed, and g, which is gravitational acceleration, is equal to 9.81. So we're gonna need those in our function later. So also here we said that we're gonna need to find the fanning friction factor, right? And we're gonna find the fanning friction factor using the Churchill equation, and Churchill equation should take the Reynolds number, right? So we're gonna so Churchill equation is the function of Reynolds number and the surface roughness. So for surface roughness, we're gonna use okay, here like 1 times like 1 e to the power of -6. Okay, it seems like something went. Okay, let's make it eg because that's what we use in our function. So for eg, we can provide it here. So it's going to be equal like 1 e to the power of -6, right? Okay, let's also run it and run our Churchill function. And this is the our givens. So our width of our rectangular channel is equal to 0.5 meters, and the flow rate is equal to 1 meters cubed per second, right? And the angle we're given is 15 degrees, but we're gonna need to use the NP sign. So NP sign is gonna use the radians rather than the degree. So we're gonna need to convert it to radians. So we're gonna multiply it by pi and divide it by 180. So if we run it, so what we originally wanted is to use the root solver, right? So the root solver has to take some function. So it has to take the function like which is right hand side function, and it's gonna solve such that the right hand side is equal to 0, right? Okay, so what we're gonna do now is, so we're gonna define an equation, and it's gonna take a vector. So, and our height is going to be the first element in our vector. So Python indexing starts from 0, so that's why it's going to be 0. And here we have to write down our derived equations. So we know our effective diameter is equal to 4 times h times w, so times over 2 plus 2 times h plus w, right? Okay, let me check if yep. Okay, yes, so we have an effective diameter now. So so here we can have our velocity. So our velocity is going to be equal to q over h times w, right? Okay, the next thing is we can write down our Reynolds number equation. So the Reynolds number, so we need the effective diameter to use in our Reynolds number, right? So it's rho times velocity times diameter divided by mu, which is the viscosity of water. Okay, and the fanning friction factor we're going to get is from Churchill equation, right? So the Reynolds number, so it's going to take Reynolds number and Eg, right? Okay. So what's the next thing we're going to do is, so our function has to return, so it has to be like here. Return our right hand side function. So we're going to use this equation, so we're going to shift this to other side, so we're going to make everything on one side, and which is going to be equal to 0, and it's going to be vector, so it's going to be g minus this side. So it's going to be, okay, let's be careful with it. So it's fanning friction factor times the q squared times 2h plus w, right? Okay, so this is our numerator. So it should be divided by, it's 2 times np dot sine of theta times h times w to the power of 3. And here I forgot like the multiplication. Okay, and this should be the lowercase. I think everything looks fine, so let's try to run it. Okay, no problems. That's cool. So now we can use the root solver. So the root solver is going to take our right hand side equation, and we also have to provide our initial guess. So we have to provide the initial guess for our height of the water, so let it be like 0.1. So if you make the initial guess, so if the difference of your initial guess and actual value is too much, it's going to cause an error. So like 0.1 is the good number. Like it's not too big and it's not too small. So let's try to run it. Okay, let's try to get so true. Okay, what's happening here? The solution converged. Okay, so yeah, we need to get the x, which is going to be equal, to 0.14 meters. So the actual height, so in this problem, we solved the rectangular open channel problem in which the water is flowing at a specific flow rate. So we derived the height of a water level using the expressions we derived from the Bernoulli's equation and the force balance of a shear using the shear stress of an alternative circular pipe, and we solved for the h. So we used the root solver from Python so that our function is going to be equal to actual d, which is 9.81, and we found specific h, which is going to make the equation equal to 0 using this root solver, and our final answer for the height of the water is going to be 0.14 meters. Thanks for your attention.